Okay, assalamu alaikum everyone, good evening. Today we're going to be talking about cholesterol metabolism. Alright, so these are just the objectives we're going to cover. Structure and function of cholesterol, how it's made and how it's regulated, and roughly what it does. Okay? So the first thing is that we have cholesterol, the molecule. You can see it over here. It's pretty cool. Now the key thing is that cholesterol is one of the essential molecules to the body. It's a membrane component, and it helps make bile, which if you remember from GIT, helps you absorb fats. It also helps make vitamin D, and it makes steroid hormones, which is stuff like testosterone, estrogen, cortisol, and stuff like that. Now, the key thing about cholesterol is that it's really, really bad at dissolving in water, which means you can't really just put it in blood and expect it to travel, like throughout the blood and spread to the tissues that it needs to go to. What that means is that we need a transport system for cholesterol. Now, to do that, what we will do is that we're going to bind it to an fatty acid. This process is called esterification, and it makes a cholesterol ester. Okay? Now, just to show you exactly what that looks like, here you have cholesterol. Now, you'll notice it has the OH bond over here at the end. And if you'll see fatty acids, you'll see it has the C, O, and then OH here. And so what you're going to do is you're going to combine them together, and you're going to get this, the cholesterol ester, which has the fatty acid, which is this stuff. And it also has the C and O, which is here, and then the O from this side. Okay? Now, I said earlier that cholesterol is really bad at traveling through the blood. Okay, so what we did is we packaged it to a cholesterol ester. The thing is, the cholesterol ester is even worse at traveling through blood. Okay, so what was the point of doing that? Well, it's pretty simple. The thing is, when we transfer cholesterol to a cholesterol ester, it becomes very easy to package into a lipoprotein. Okay, so let me just show you what that looks like. And just before that, I want to show you a small thing. Ooh, sharing is gone. Okay, so you can see here that fatty acid is like a massive, massive molecule. And cholesterol is also pretty big. Okay, so because these are they're basically very big molecules, they're very chunky, they're not going to travel well through the body. They aren't going to travel well through the blood. Okay, so what we do instead is, if I go back to the slideshow, we package them like this, right? Now this is what it looks like when cholesterol is not converted into an ester. You get this disc-shaped thing, which is nice, but we can do better. And so once you convert it to an ester, it turns into a sphere, it turns into a ball, which is very, very good at traveling through the blood and helps make things a lot simpler. Okay, so that's what's being said here. Cholesterol esters are more hydrophobic than cholesterol, they travel worse. And so what they're going to do is they're going to leave the surface and go inside the core where you're going to get cholesterol esters. That's CE over here. Okay, so they'll travel into the middle of HDL and become the core of HDL, and it will travel very easily in the blood. Okay, so where do we get our cholesterol from? Now, the key thing is that you eat cholesterol. You eat it in your food. You'll get it, for example, from eggs. You can get it from meat. Now, when you eat cholesterol, you're only going to absorb about 50% of the cholesterol you eat. So, for example, an egg, let's say it's 50 grams of cholesterol, you're only going to get 25 grams from that. Okay, that's obviously a wild exaggeration. You're never going to get that much cholesterol from eggs, but I think you can get the point. Now, what happens is that cholesterol is taken from the intestines, it's put in chylomicrons and chylomicron remnants, which move cholesterol to the liver. Okay? Now, the more you eat cholesterol, the less you're going to absorb. Right? Like the less in terms of percentage. And overall, the body will try to get rid of 1 gram of cholesterol in a day in the form of bile acids. Okay? So, the other place that the liver can get cholesterol is from extrahepatic tissues, such as like fat storages all over the body, right? And so what happens is that you're going to get reverse cholesterol transport from the adipose tissue to the liver. And the thing that's responsible for doing that is HDL, chylomicron remnants, and IDL. And the third place you can get cholesterol is by making it de novo, or making it inside the liver itself. Okay, so let's just really quickly talk about what chylomicrons are, because the lipoproteins lecture is the one after this. Yeah. So this is a chylomicron. You can see that you have cholesterol in the middle, and you can see that it's wrapped in these proteins, which make it very good at traveling throughout the body, as opposed to the very chunky molecule of cholesterol, which isn't going to dissolve well. So these proteins help transport cholesterol throughout the body. Now you can see here that HDL has a lot more cholesterol than chylomicron, which is what makes HDL very, very good at transporting cholesterol, and that's what helps it bring the cholesterol back to the liver. And the other thing is that that's why we want to have HDL in the body, because it's so good at transporting cholesterol that it's not going to get stuck in your blood vessels the way LDL does. Okay? Now, let's say that you eat 400 milligrams of cholesterol in a day. Right? Now, we said earlier that you're only going to absorb about 50% of it. So, 400 milligrams of cholesterol eaten, and you're only absorbing 200 milligrams, which is 50%. Overall, you're going to release 1,000 milligrams as bile into the intestines, which helps do what bile does. Which means is if you take 1,000 milligrams, subtract the 200 that you got from your food, you're making 800 milligrams inside your body. What that means is if you lower your dietary cholesterol, your blood cholesterol isn't really going to change, since most of it is made inside your body. And this is why you'll notice nutritionists nowadays have stopped recommending that you lower dietary cholesterol, because it just doesn't work that well. There are other strategies that we use for the diet, but lowering cholesterol on its own isn't very good at lowering your blood cholesterol. Okay, so this is what reverse transport looks like. You have the adipose tissue over here, for example, and you're going to package the cholesterol into HDL, which is going to travel to the liver and dump that cholesterol into the liver. Okay, and there's two enzymes that help out with this. The first one is LCAT, which takes the cholesterol and puts it into the HDL. And the second enzyme that helps is CETP, which takes the cholesterol from HDL and puts it into LDL. Now you'll notice I mentioned that LDL has a tendency to get stuck, which is not very good. And that's why CETP is kind of an iffy enzyme we don't really want to active. But the key thing is that it's involved in cholesterol transport. So we have two enzymes involved in cholesterol transport, LCAT and CETP. Okay, so this is just to recap where you can get cholesterol. I'm going to take a couple questions. Okay, so the reason why cholesterol esters are transported more easily is because, if I go back a couple of slides, so you see here, you have cholesterol on the surface of the disc. That makes this disc not very good at traveling through the blood. If we convert it to a cholesterol esters, the ester is going to hide inside the middle. And because it's going to hide, it's going to make the shape more spherical, which is better at transport. So yes, the proteins do help to transport, but the key thing is the change in shape. Does that answer the question? Okay. So, just to recap where you're getting your cholesterol from, the first place is from your food, which is going to be taken to the liver in chylomicron remnants. The second place is cholesterol that's made in adipose tissue, in fat tissue. That's going to be taken to the liver through HDL. And the third way is making it in the liver, de novo. All right? And this is just showing the functions, or like what happens to cholesterol after it's made, such as secreted with bile, made into bile, and put into VLDL. We're going to be talking about the making of bile in a bit. So don't worry if that doesn't make too much sense. Okay, so cholesterol biosynthesis. Now, this is a bit of a wordy slide, but I'll try to break it down for you. Okay, now the key thing is that when you're making cholesterol de novo, what this means is that you're making it inside the cells instead of recycling it. This process starts with acetyl-CoA, and we're going to look at the process later, but the key thing is that because it starts from acetyl-CoA, you can get it from glucose through the glycolysis pathway. You can also get it from oxidation of fatty acids. The third way you can get it is through oxidation of amino acids. Okay? So there are three sources of acetyl-CoA to make cholesterol: beta oxidation of fatty acids, pyruvate from the glycolysis pathway, and amino acids. Okay? So that's the first thing you need for the cholesterol synthesis, acetyl-CoA. The second thing you need is you need NADPH. What NADPH does is it has this H over here, which represents hydrogen. So the hydrogen allows NADPH to have reducing power. And here's just a small hint. Anytime you see NADPH, that means we're making something in the body. Okay, so NADPH comes from the pentose phosphate pathway, as you've probably taken before. And the final thing you need is, of course, energy, because we're making a big molecule from small molecules. Okay, so where does cholesterol synthesis happen? It mostly happens in the liver. So that's where all of this fancy taking of acetyl-CoA, taking of NADPH and energy and combining them into cholesterol will happen. But it can happen elsewhere, such as the intestine, the skin, and it can also happen in the adrenal gland. Okay? Now, like we mentioned, it mostly happens in the liver. And this is the overall equation. You're going to need your acetyl-CoA, you're going to need your energy, you need your NADPH, and oxygen. All right. So this is a very big graph, and it looks like it has a lot of details. But from the lecture, the doctor mentioned that he only wants you to focus on these molecules that have a box around them. Okay. So the main source of carbon for cholesterol comes from acetyl-CoA. And everything else sort of helps along, such as the energy, NADPH, and oxygen. Okay, so the main steps that you need to know is that you need to know that we have acetyl-CoA at the start, and then we make this molecule, which I'm not going to try to pronounce, because the short term for it is just HMG-CoA. So like HMG and then CoA. All right, and this is reduced by the enzyme HMG-CoA reductase into mevalonic acid. Okay, and then from mevalonic acid, we're going to first convert it into a C5 molecule, and then we're going to start stacking these C5 molecules until we form squalene. Okay, and that's what you see here. So you have 6 of these 5 carbon molecules combined together form squalene, and that's where you see 30 carbon molecules over here. The final step is just converting squalene into cholesterol. Okay, so 4 steps that you need to know. The first one is you make HMG-CoA, then you reduce it to mevalonic acid, and then you make squalene from mevalonic acid by first converting it into C5 and then stacking those C5 together. And the final step is you make cholesterol from squalene. You don't need to worry about all of this stuff in the middle. That's basically just filler. Okay, so like we said before, the making of cholesterol is a very, very regulated enzyme. Okay, and the key enzyme that we use to regulate cholesterol synthesis is HMG-CoA. Reductase is HMG-CoA reductase. Why? Because it's the rate-limiting step of cholesterol biosynthesis. All right, now there's 3 ways we can regulate HMG-CoA reductase. The first one is by phosphorylation. The second one is by degrading the enzyme by completely breaking it down. And the third one is gene expression. So gene expression will control how much new HMG-CoA reductase we make. And because we can control how much HMG-CoA reductase we make, we can control how much cholesterol we're making. So this is what that looks like with phosphorylation. Okay, so first we're looking at what insulin does. Now, what does insulin do in the body? Insulin will rise as you eat glucose. The higher glucose you have in your blood, the more insulin you'll have in your blood. Now, because having a lot of glucose in the blood is bad, we want to store this glucose. We want to store this energy. And one of the ways we store it is as cholesterol, by converting it into acetyl-CoA and then converting acetyl-CoA into cholesterol. So, what insulin will do is, as insulin goes up, it will activate the enzyme HMG-CoA reductase, which allows you to make more cholesterol. So as we said, glucose goes up, that makes insulin go up, which activates HMG-CoA reductase by dephosphorylating it, by removing this phosphate here. And then you will make more cholesterol. Now, the reverse of that happens if you have low glucose. If you're fasting, you're going to have high glucagon, which will activate this enzyme protein kinase A. And so that's going to phosphorylate cholesterol. So you're going to make less cholesterol, because if you don't have glucose, you don't want to be wasting the glucose that you do have on making cholesterol. All right? So that was one of the ways that we can control cholesterol synthesis. The other way is through controlling the transcription and translation of the enzyme. So as you can see here, if you have cholesterol being put into the cell, so this is cholesterol esters, which gets converted into cholesterol, which is over here, you're going to have a lot of cholesterol. That does three things. The first thing is you're going to make less HMG-CoA reductase, and so you'll make less cholesterol. The second thing is that you're going to increase this ACAT enzyme, which helps you store more cholesterol inside the cell. And the final thing is you're going to have less LDL receptors on the cell over here. And so what this is basically saying is the cell is telling you, I've taken a lot of cholesterol from outside. I don't need to make more cholesterol, which is over here. I need to store this cholesterol that I have, which is by ACAT. And I don't want to take any more cholesterol in, which is by lowering LDL receptors. Now, the final thing is that how do we get rid of cholesterol? The first way is that it can be transferred into feces, but the key thing that we want to look at is this conversion into bile salts. Okay, now, before we look at bile salts, one thing that was mentioned was statins. Statins are a drug that we give to patients that have high cholesterol, because what it does is it will compete with cholesterol for the HMG-CoA reductase. So it will compete with HMG-CoA for the reductase enzyme. And so because they're going to be fighting with each other over the enzyme, you're going to have less cholesterol made. This drug is pretty good, these statins, which is Mevacor and Lipitor. They're pretty good at competing with HMG-CoA, so you're going to get a 20 to 40% decrease in cholesterol. Now, let's look at some disorders. Let's look at some disorders of patients that have high cholesterol. So the first one is familial hypocholesterolemia, which is where you're going to have low LDL receptors on your cells. So we mentioned here that you have LDL receptors on the cells, which are going to take the cholesterol in. If you don't have those receptors, you're going to have high cholesterol in the blood, which is going to lead to coronary artery disease. Okay? Now, the first type is heterozygous, which is when you only have one gene for LDL receptor deficiency, and this isn't that rare. Okay? It's pretty common. It's 1 in every 250 people. The homozygous version is very, very rare, and that's why you're going to get very high cholesterol in the blood, and you're going to get a very early coronary artery disease. And just one thing to note is that it's equal between men and women, and the mutation for this disease is recessive. How do we treat it? Well, the first way is that we do dietary interventions. Okay, we try to encourage the patients to lose weight. We try to encourage them to exercise. The second way is is that we try to give them drugs that are going to lower their cholesterol. And for example, we mentioned statins, which at the highest dose can cause a 60% reduction in cholesterol in the blood. Okay, so I mentioned that one of the ways that we get rid of cholesterol is by making it into bile. So what is bile? Bile is a watery mixture, and it includes bile acids and bile salts, as well as phospholipids. And so what you're going to do is you're going to take this cholesterol, you're going to convert it into these bile acids. Okay? And so what these can do is they're pretty good at binding to fats, and so it'll help you absorb fats inside the small intestine. All right, now once you do that, once they've done their job in the intestines, they've helped absorb the fat, they're going to go back into the liver and get conjugated with proteins. In this case, you can see that we have glycine, the glycine protein here, and the taurine protein. This makes it into a conjugated bile salt. Conjugated bile salts are even better than acids at emulsifying and absorbing fats, and so they're very good. They're very good to help absorb fats for the body. This is a diagram just to help show you that you have your bile acids and your bile salts. They're going to be released into the intestines, and then they're going to help bind to fats, emulsify the fats, and then reabsorb just to go back to the liver. Of course, you're going to lose a couple of them, so that's 0.5 grams, which will be lost in the feces. The reason this matters is that some patients, especially those that have high levels of cholesterol in the blood, will have cholelithiasis, right, which is gallbladder stones. You can see these stones in the picture. Okay? Now, one of the ways that you can see it is if you're releasing a lot of cholesterol into the intestines, such as patients that take fibrates, but you don't have to worry too much about this point over here. The other way that can happen is that if you're obstructing the bile duct, because if the bile duct is blocked, all the cholesterol is going to stack inside the gallbladder and it will form stones. And so the way you treat it is by a cholecystectomy, which is just you open the patient, you take out the gallbladder, and then you call it a day. The thing about cholecystectomies is that now you're not going to be absorbing as much fats. And so what you'll see in people that you've removed, who've had their gallbladder removed, is that their feces are going to be very, very fatty. And so they're going to have a lot of steatorrhea, which is fatty diarrhea. And they're going to have very, very bad smelling feces. Now, the final thing that we mentioned for cholesterol is that it helps make steroid hormones. There are a bunch of steroid hormones, such as glucocorticoids, which help regulate the levels of carbohydrates in the body. It helps regulate your blood sugar. The second one is mineralocorticoids, such as aldosterone, which helps regulate sodium and water. And the final one is gonadal steroids, such as testosterone and estrogen. Okay? Steroids have a lot of functions in the body. They are basically one of the most powerful substances that you can give someone, which is why they're used so much to cheat in sports, because they can help control bone metabolism, fitness, behavior. They can control inflammation, stress. If you give someone steroid hormones, those hormones will practically do everything to the body. Okay? But of course, just like cholesterol, these steroids are very, very bad at being transported through the blood. And so we have globulins, we have these proteins that help bind to these hormones to carry them. So we have corticosteroid binding globulin, which carries cortisol, which is a glucocorticoid. And we have sex steroid binding globulins to carry testosterone and estradiol, which is estrogen. This is just going over the types again. So you have glucocorticoids, such as cortisol and cortisone. Cortisone is the active metabolite of cortisol, and it's what you're going to give as a medication to a patient that needs cortisol. You're going to give them cortisone. The second category is mineralocorticoids. Like we mentioned, that's aldosterone. It helps control sodium and water levels in the body. Then you have androgens and estrogens, which are your sex hormones, and finally progestogens, such as progesterone, which is also participates in as a sex hormone. Like we said, cholesterol makes the steroid hormones. This process happens inside the mitochondria and the smooth endoplasmic reticulum. And the key thing is that you never ever package steroid hormones. You just make them and then immediately release them. All right? This is just the basic overview of the synthesis pathway. Okay. So you have the rate limiting step. There's just a very small mistake that I'm going to correct here. Okay, back to the slideshow. And we're all going to pretend we didn't see that. So the rate limiting step of steroid hormone synthesis is moving the cholesterol into the mitochondria. Okay? Which the way this happens is through this protein, the star protein. Okay? And so what you're going to do is you're going to make cholesterol inside the cell or outside the cell, like you might take it in from outside, and then it's going to be moved into the mitochondria by the star protein, and then from there you can make the hormone. The key thing that the doctor wants you to focus on from this graph is just the star protein over here, which is going to move everything into the cell. Now, this is a list of enzymes that participate in the steroid hormone synthesis pathway. There are 5 enzymes that you need to know, which are these 4 down here, and the side chain cleaving enzyme desmolase, okay, which is the SCC enzyme that you see here. So these are the ones that you need to know, right? You just need to know their names basically. But the ones that we're going to focus on for the lecture, and the ones that we're focused on the most during the actual lecture, and that you're most likely to be asked about for your MOL final, are these 2 enzymes over here, 21 alpha hydroxylase and 11 beta hydroxylase. And these are just the names of those enzymes. So here we have the process of making the steroid hormones. You can see that we have those 2 enzymes highlighted, A2 and B1, because they're the enzymes that you need to focus on. And the other thing that you need to focus on is these 2 compounds. I'm going to be honest with you, this diagram is kind of dense, it's kind of packed, and it's very confusing. So I made it a simplified version over here. So you have cholesterol, and then it's converted into pregnenolone. From there, you have 2 options that it can do. It can either go to progesterone, or it can continue down to make either androgens or 17-hydroxyprogesterone, which is the first compound that you need to know. If it does make progesterone, it can continue down to make aldosterone by going through deoxycorticosterone, or it can convert into 7-hydroxyprogesterone to make cortisol. Okay? The third option is, like we mentioned, is that it can go into the androgen synthesis pathway, and it can make estrone, testosterone, which is your androgen, or it can make estrogen later. Okay, so the other thing that he wants you to know is that you make testosterone first, and then you make estrogen. All right, so let's look at the 2 deficiencies that we want to look at. The first one is 20-alpha hydroxylase deficiency, which will block the process at this level. All right. Now, in both of these disorders, you're going to have high levels of estrogen and high levels of androgens, right, which is testosterone. In both of these disorders, the key thing that separates them is these molecules over here. So in 21-alpha hydroxylase deficiency, you're going to have the cholesterol go down, and then it's going to get stuck at progesterone. And so what the body does is it will just convert it to hydroxyprogesterone, and you're going to have a lot of this in the blood. Okay, but if you have 11 beta hydroxylase, it's not going to get stuck at this stage. Instead, it's going to keep going down and get stuck at this level, which is deoxycorticosterone. Okay, so that's the key thing. In 21 alpha hydroxylase, you'll get high levels of 17-hydroxyprogesterone, and in 11 beta hydroxylase deficiency, you're going to get high levels of deoxycorticosterone. Okay? So the first one is the 21 alpha hydroxylase deficiency, which we mentioned over here. It's autosomal recessive. It's the most common one it's the most common cause. So what happens is that if you look here, because you're blocking at this level, you aren't going to get aldosterone and you aren't going to get cortisol. Okay? And so what the body will do is it will keep signaling. It will try to keep signaling to make these hormones, and the signaling molecule we use is ACTH. But because you're continuously releasing ACTH, the adrenal gland is going to, which is responsible for the steroid hormone synthesis, is going to keep trying, but because it can't, what's going to happen is that the adrenal gland is going to grow. It's going to become a lot larger. Okay? And like we said, what that's going to do is it's going to divert the cholesterol into making estrogens and androgens. Now, in severe cases, because you don't have aldosterone, and because you don't have aldosterone, which is very, very important to help maintain blood volume, what you're going to get is you're going to get hypovolemia and shock. And so what this will look like is you'll have a baby that has very, very low blood pressure. Okay? Now, if the patient doesn't have that severe of a hydroxylase deficiency, they might still, they're still going to show symptoms of low aldosterone, but obviously they're going to present much later. So, as we mentioned, you're going to have high levels of 17-hydroxyprogesterone, and that's how you diagnose it. So you look at the patient's plasma, you look at the patient's blood, you try to see if you can find the 17-hydroxyprogesterone. If you find a lot of it, that means they have 21-hydroxylase deficiency. And some of the side effects you'll notice as well, because you have high androgens, is you're going to have virilization in baby girls, which is they're going to be very masculinized, so they'll have facial hair, body hair, they're going to have acne, they're going to have very deep voices, and they're going to be very muscular. Okay? And in boys, what will happen instead is they're going to hit puberty much earlier. Okay? And in the case of patients that don't have a full deficiency, they only have a partial deficiency, that's just going to look like hirsutism and menstrual irregularity. So that's an irregular period, and you're going to have a lot of excess facial hair in young females. Now, the second deficiency that we mentioned is 11-beta-hydroxylase. All right? And so what that's going to look like is you're going to get high levels of deoxycorticosterone. Okay? You do also get high levels of 11-deoxycortisol, but that's not as important, and it's also not what you're looking for. What you will look for is 11-deoxycorticosterone, which is going to be very, very high. The important thing is that this molecule, 11-deoxycorticosterone, can act as a mineralocorticoid, but it's not as good. It's not as good as aldosterone at doing the mineralocorticoid work. And so obviously, so you're going to have a lot of mineralocorticoids. What that's going to look like is you're going to have a lot of salt in the patient, you're going to have a high volume, and you're going to have hypertension. Okay? Because you have a lot of ACTH being made because the body still can't make aldosterone and it still can't make cortisol. So the body is still trying to tell the adrenal glands, hey, I need these steroid hormones, I need you to make them. And so what's going to happen instead is you're going to get a lot of deoxycorticosterone, which is like 11-deoxycorticosterone. And so you're going to get a lot of it, which will cause hypertension, salt retention, and hypovolemia. And of course, the other thing is that you're going to get very muscular males and virilization or masculinization of females. Okay, and that's it. If you have any questions, I'll be more than happy to take them. But if not, I think that should be it.